Hi chemistry students, this is Dr. Lesher and this video is to give the roadmap and some of the first information on chapter 16, which is the spontaneity of reactions. So the way I'm going to structure these lessons might be a little bit different from what Dr. Malpi was doing. We'll be basically dividing this chapter into three lessons or three sections. Lesson 1, which will be for Monday, April 6th, is the introduction and background on entropy. Lesson 2 will focus on free energy and the meat of this chapter, spontaneity. That'll be for Wednesday. And then lesson 3 won't fall until after the Easter break, so Wednesday of next week. So for this lesson, a few objectives for you guys. The first is to be able to discuss the second law of thermodynamics and really to be able to employ kind of multiple ways of explaining the second law. Then to define and describe entropy in terms of both probability of microstates, which we'll get into, and by using some simpler analogies. And then we want to be able to compare entropies of different substances, considering things like quantity and phase and temperature. And finally, we'll begin to quantify entropy changes during reactions and physical changes. So a little bit of context for this chapter. You may have heard of the first and second law of thermodynamics. If not, that's okay too. The first law is that energy is conserved in the universe. Another way to say that is that you can't get something for nothing in terms of energy and work. The second law of thermodynamics is that you're always losing useful forms of energy. Now, that might seem a little bit counterintuitive considering that first law, but yeah, useful forms of energy are constantly being dispersed into that larger universe. Another way to state this is that entropy increases, and we'll define entropy much more carefully shortly. Another way to define it is that things become more disordered or dispersed. And then perhaps my favorite way to think about this second law of thermodynamics is that things wear out. Your new sneakers, they wear out eventually. You can't really unwear them out. You can't really unfry an egg. So as things change, sometimes those processes are irreversible. Now, this also might be counterintuitive because there's a whole lot of really organized structures in the world, in the natural world and in the human world. From a bee's honeycomb to the buildings and highways that we build, to cells in plants and the things that they can do. Furthermore, how plants grow by taking in carbon dioxide from the atmosphere, which as a gas is really dispersed. And some of that carbon is incorporated into the structure of the plant cells. These are definitely the opposite of things becoming more dispersed. So how do we reconcile all of this? Well, we're not always making everything more disordered because processes are reversible. And so this is where the concept of spontaneity comes in, and we'll tie it back in a little bit more closely to the chemistry perspective here. In everyday speech, spontaneous means events that just take place without much work. So a ball rolling down a hill, that's spontaneous. In chemistry, a spontaneous reaction is one that favors the products of that reaction under the conditions of that particular reaction. And many of these reactions can be reversed, but that requires some outside force. So ice melting, clearly that's something spontaneous if it's occurring at room temperature. Nails rusting, this is a pretty slow process, but your nails will eventually get rusty if left out in the atmosphere, and you can't really unrust them very easily. You can take iron oxide and convert it to iron through some chemical reactions that require inputs of energy. Same thing with the ice, you can freeze it by putting it back in the freezer. But the spontaneous direction is only one way. So let's look at a really simple example. If we have a cup of coffee and we put a sugar cube in there, that sugar cube will dissolve. That's another example of a spontaneous change, the dispersal of those molecules of sugar. Furthermore, we've got heat coming off that coffee cup as well. And so energy is also dispersing in this example. Our cup on the right is quite a bit cooler because it's lost some of its heat to the surroundings. Let's look at the ice melting a little bit more carefully now. So we know that ice melts spontaneously at 25 degrees C. If we just have a cup of ice water on the table at 25 degrees Celsius, room temperature, it's going to melt. What is happening in terms of dispersal when the ice in that cup of water melts? Well, if we think about the molecules of water, at first they were constrained in that ice cube, but once melting occurs, they're dispersing into that larger cup of water. Energy did have to be absorbed by that ice cube. If you remember back to last semester, melting is an endothermic process. We need to put heat into that ice cube to make it melt. So our energy is actually becoming more constrained because it's moving into that cup of water and ice. So here we actually kind of have some trends that are counter to each other. Let's think about the opposite process as well, just to really wrap our heads around this. Water does freeze spontaneously if you put it in the freezer. And in that case, our liquid water is becoming a solid. Those molecules are becoming less dispersed or less disordered or more ordered. You kind of think about it anyway. And the energy is being pulled out of that system. This is another one that's a little bit counterintuitive, but if you've ever put your foot near, the fan that's pushing the heat out of the freezer, freezers put off quite a bit of heat, and they have to be able to pull heat out of the tray of ice that you just put in there, or if you put some leftovers in the freezer, that heat has to be removed. So freezing is an exothermic process. That energy has to leave the system. So yeah, these are dispersal trends that are opposite each other. Our water during freezing is becoming, the matter is becoming more constrained while the energy is becoming more dispersed. So this tells us a couple things. If we're trying to figure out whether the process is spontaneous or not, we have to consider both the dispersal of matter and energy. And we kind of need to consider both the system and the surroundings. Another thing is that these processes may be temperature dependent. So, of course, ice cubes melting is spontaneous at room temperature, but not if you're in the Antarctic. We're going to be able to assess the spontaneity of reactions by the end of next lesson by quantifying enthalpy changes. Enthalpy is covered up probably by my video here. And entropy changes in a reaction. Enthalpy changes you learned about last semester, so we'll be pulling some of that back, and I'll go over it if it's something that's rusty for you. And entropy changes we're going to start to quantify very shortly here. So the next part of this lesson, I'm actually going to direct you to a YouTube video that I think is really great to start your definition of entropy, and then we'll recap it in the next part.